Okay, so for each problem, we want to set up but not evaluate an integral to find the indicated volume. Find the volume of the solid generated when the region enclosed by y equals square root x, y equals 2, and x equals 0 is revolved about the y-axis. So square root x, that has 0, 0, 1, 1, 4, 2. Those are points on square root x, so I'll sketch that in. Okay, and then the next line is y equals 2, so that's a horizontal line. Y equals 2, and x equals 0, that's the y-axis. So I have this region enclosed by those three curves. All right, and I want to rotate that region about the y-axis. So it's going to go like that. Okay, so I'm going to pick a representative rectangle that's perpendicular to the axis of revolution. So I'm going to draw a random rectangle here. Okay, and I randomly chose a spot along the y-axis to draw that. So we're going to call the location of this rectangle y sub I. And when I take that rectangle and rotate it about the y-axis, it's going to create a disk. So I'm going to draw a picture of my disk. It's got some radius r. That is the length of that rectangle. Okay, so the length of that rectangle, that is an x value. I need to know this location on the x-axis, given a generic location y on the y-axis. So I have an equation that relates y and x for this curve, right? Y equals square root x. So if y equals square root x, I'm given y and I need to know what x is, right? So I'm going to solve for x and I get x is y squared. Y squared. So that is my radius, capital R is y squared. And then the thickness of this rectangle is going to be the thickness of my disk, which is a small change in y. That is this distance is a y distance. So the volume of my disk is pi r squared times thickness. And my r is yi squared. And my thickness is delta y. And the volume of all the disks is the sum where each disk has this volume. I goes from 1 to n. So I'm going to have n disks and add them all up. And then my volume exact is the limit as n goes to infinity of this sum, which is the definition of an integral. So I'm going to calculate, this is going to be pi y squared. I'm just converting. I dropped the subscript of I and I changed the delta y to a dy. And then my bounds of integration, I have to think about where am I stacking up these disks. So all along the y-axis, I'm building these disks where I have these rectangles that are then going to get rotated around the y-axis, and I'm creating these disks. So I've got these disks that I'm stacking up along the y-axis. And so I'm starting my stacking at 0, and I'm going to finish at 2. Y equals 0 to y equals 2. So those are my bounds of integration. Okay, find the volume of the solid generated when the region between the graphs of 1/2 plus x squared and x equals 0 and x equals 2 is revolved about the x-axis. Okay, so f of x equals 1/2 plus x squared. So that is going to be 0, comma a half, 1, comma 1.5, and 2, comma 4.5. There's my f of x. And then g of x is x. So that would be 0, 0, 1, 1, 2, 2, 3, 3. Okay, and I want to, then I have some other bounds, x equals 0 and x equals 2. So that's here to here. So this is my region that I am rotating about the x-axis. Okay, so I'm going to pick a random location between x equals 0 and x equals 2, somewhere in my region. We'll pick it right here. This will be x sub I. I'm going to draw a rectangle at that x location. Representative rectangle. So this purple rectangle is my representative rectangle. It's going to rotate about the x-axis. So it's going to create a washer. So my rectangle is going to end up, when I reflect it over the axis of revolution, it's going to look something like this. And I have this washer. Okay, so I need to know the inner radius and the outer radius of the washer. So my inner radius is the distance from the center, the axis of revolution, to the bottom of that representative rectangle. And that representative rectangle, its bottom is on the green line here, which is the line y equals x. So that distance is a y value which is x sub I. So let's see, I'm going to draw my washer. My inner radius is x sub I. So at x sub I, this is an equal distance up, x sub I equals y sub I. Okay, and then my outer radius is the distance from here, let's do this in another color, here to the center. So this distance. So that is going to be 1/2 plus xi squared. So the volume of my washer is pi times the outer radius squared minus pi times the inner radius squared. Now I add up the volumes of all my washers. So it's just the sum as I goes from 1 to n of this. And then my exact volume is the limit as n goes to infinity of my sum of this. And then that is the definition of an integral. So this is the integral, and I'm going to translate by dropping the sub i's and changing my delta x to a dx, which makes me realize that I did not multiply times delta x. There we go. Okay, so this becomes pi times 1/2 plus x squared minus pi x squared dx. And my bounds of integration, I have to think about where am I stacking up these washers. So I'm going to go back to my picture, and I drew one representative washer here, but I'm starting at 0 and going until 2. At every location x sub I here, I have all these representative rectangles that when I sweep them around the x-axis, I get a washer. So I'm stacking these washers up from x equals 0 to x equals 2. So my bounds are 0 to 2. All right, the region bounded by y equals square root of x plus 1, y equals 0, x equals -1 and x equals 1, rotated about the x-axis. Okay, so square root of x minus 1. If I plug a -1 in there, I get 0. If I plug a 0 in there, I get 1. And if I plug a 1, I get the square root of 2. I'm just going to estimate from my picture here. There's y equals square root of x plus 1. And then y equals 0, that's the x-axis. And x equals -1 and x equals 1. So this is my region here, shaded in purple. And I'm going to rotate that region about the x-axis. All right, so I'm going to pick a random spot along the x-axis to draw a rectangle perpendicular to the x-axis, my axis of revolution. So let's see, I'll pick this spot right here, and we'll call it x sub I. I'm going to draw a rectangle at x sub I, shade it in. It's got a little bit of thickness, delta x. And I'm going to rotate that rectangle about the x-axis, and I'll get a disk. And the height of that rectangle is the radius of the disk, and the height of that rectangle is the height of the function y equals square root x plus 1. So the volume of my disk is pi times the radius of the disk, which is the square root of x plus 1 squared, times the thickness of the disk, which is delta x. The volume of all the disks is the sum from I equals 1 to n of pi times the square root of x plus 1 squared is just x plus 1, delta x. And then my volume exact, I take a limit as n goes to infinity of the sum from I equals 1 to n, pi times x plus 1, delta x. That is the definition of an integral. It's a limit of a Riemann sum. So this is the integral. I translate, dropping the subscripts, which I forgot to put in the first place. There we go. Drop the subscripts, change the delta x to a dx. So this becomes pi times x plus 1 dx. And then for the bounds of integration, I drew one representative rectangle on here to figure out its volume, the volume of the disk. But I'm actually drawing lots of these rectangles along the x-axis here, starting at x equals -1 and finishing at x equals 1. Those are my bounds of integration. Region bounded by the curves y equals x squared, rotated about the line y equals 2. Okay, so y equals x. I've got 0, 0, 1, 1, 2, 2. There's my line y equals x. Connect those. And then y equals x squared, so that gives me 0, 0, 1, 1, and 2, 4. So I'm going to connect those with a nice smooth curve. I know it looks like a parabola. So I want the region bounded by these two curves. So this is kind of tricky. So I have this area that's bounded between those two curves. And then I have this area in green between the two curves, but this area in green is unbounded. It just keeps going and going and going. So this is not what I'm interested in, not the area of interest. Because the question used the word bounded, the area bounded between the two curves. So it's this pink area because it is not an unbounded area. All right, so that's my area, and then I want to rotate it about the line y equals 2. So let's draw that in. That's a horizontal line, y equals 2. My axis of revolution. Okay, so I'm going to draw a rectangle in my area, representative rectangle. picking a random place to put it, some xi value, and I'm going to rotate it about the axis of revolution, and the reflection will be somewhere up here, and I get a washer. And I have to think about its inner radius and its outer radius. So the inner radius is the distance from the center, which is the axis of revolution, to my representative rectangle, the closest distance to the representative rectangle. So that is my little r. And little r is the distance from 2 to the line y equals x. So 2 is bigger, so it's just 2 minus x sub I. And then my big R, that is the distance from the center to the far end of my representative rectangle. That's my big R. So that's the distance from y equals 2 to y equals x squared. 2 is on top, so you just do the top minus the bottom. So it's just 2 minus xi squared. So the volume of my washer is pi times big R squared minus pi times little r squared all times the thickness of the washer, which is delta x. And then I'm going to add up all my washers. So it's the sum from I equals 1 to n of all the washers that have that volume. And then my volume exact is the limit as n goes to infinity of the sum of all the rectangles, n rectangles, which is the definition of an integral. Oops. So this equals the integral, and now I'm going to drop the x sub i's. So I have pi times 2 minus x squared squared minus pi times 2 minus x squared. And instead of delta x, I use dx. And then for the bounds of integration, I'm going to go back to my picture and think about where am I stacking these washers. It is along the x-axis, starting at 0 and ending at 1. That's where I'm drawing all these little rectangles that are all going to get rotated about the line y equals 2, forming washers. So I have all these washers being stacked up between x equals 0 and x equals 2. Those are my bounds of integration. Okay, the region bounded by y equals sine of 2x and the x-axis between x equals 0 and x equals pi over 2. We're going to revolve that around the x-axis. Okay, so sine of 2x, well, the sine of 0 is 0. If I plug a pi over 2 in, that's the sine of pi, which is also 0. Plug in pi over 4, that's the sine of pi over 2, which is 1. And then halfway between, I have changes in concavity. So this looks something like that. And I'm going to rotate that about the x-axis. So I'm going to draw a representative rectangle. Pick a random spot along the x-axis. We'll call that x sub I. And I'm going to draw a rectangle. Rotate that about the x-axis. It's going to sweep out a disk that has some width delta x. And the radius is just the height of this rectangle, which is sine of 2xi. So the volume of my disk is pi times the radius of the disk, which is sine of 2xi squared, pi r squared, times the thickness, delta x. So the volume of all the disks, I'm just going to add up all the disks that have this same volume formula. And I'm going to rewrite this as sine squared and i's going from 1 to n, and then the volume exact is just the limit as n goes to infinity of the sum of all the disks. That is the definition of an integral. Translate by dropping the subscript i's and change the delta x to a dx. So this is pi times sine squared of 2x dx. And my bounds of integration, I have rectangles that I'm sweeping around the x-axis to form all these disks. I'm stacking up these disks starting at x equals 0 and going to pi over 2. 0 to pi over 2. Okay, last one. The region bounded by the curve y equals square root x and y equals 0.1x between x equals 0 and x equals 4. So y equals square root x, so we've got 0, 0, 1, 1, 4, 2. That should be good enough. Just connect those. Y equals square root x. Y equals 0.1x. Okay, so if I plug in a 5, well, 0, 0 is on there. And if I plug in 5, 0.1 of 5 is 0.5. So that's my next point. And I'll connect those with a straight line. Y equals 0.1x. And I want the region bounded between those two, x equals 0, which is right here, and x equals 4, so right here. So this is my region that I'm going to rotate about the x-axis. So let's draw a representative rectangle at a random x value between 0 and 4. Pick this one right here. We'll call this x sub I. And I'm going to draw a rectangle at x sub I. It has a little bit of thickness, delta x. And I'm going to sweep that rectangle around the x-axis, and it's going to sweep out a washer. So sometimes it's often helpful to draw the reflection. Goes to a little past 1.5. Draw the reflection of the rectangle, and then you can more easily picture the washer. Okay, so I need the inner radius and the outer radius of this washer. So the inner radius is the distance from the center, which is the axis of revolution. So the distance from the x-axis to the bottom of my representative rectangle, the closest point of the representative rectangle. And that is on the line y equals 0.1x. So little r, my inner radius, is just 0.1x. And then big R is the distance from the center, different color, from the center, the x-axis, to the furthest distance on my representative rectangle. So this distance, which is y equals square root x, the distance from the x-axis to this point, which is on the graph y equals square root x. So big R is square root x. So the volume of my washer is pi times big radius squared minus pi times little radius squared delta x. Then I'm going to add up n of those washers and then take the limit as n goes to infinity. So the volume of all the washers is the sum from I equals 1 to n, where each washer has that volume. And then the volume exact is the limit as n goes to infinity of the sum of all the washers, which is the definition of an integral. So square root of x squared, that's just x. So this is going to be pi x minus pi times 0.01 x squared. And then my delta x becomes a dx. And my bounds of integration are going to be 0 to 4, where I'm stacking up these washers.